Hi, what's up? I hope everything is good on your side. Please stay healthy and safe during this insane situation, and I'm sure that we can solve this coronavirus problem with solidarity and uniting very soon. Today I'm going to give you a good insight about the paper priming BERTology, what we know about how BERT works. It's a work by Anna Rogers, Olga Kovaleva, and Anna Romshinsky. I hope that I pronounced their name well, and it was published recently in Archive 2020. My name is MojtabaValipour, and I'm a PhD student of computer science at Data Analytical Lab, and this is a presentation for CS886 course of Deep Learning for NLP by Professor Ming Li at University of Waterloo. My presentation was divided into four major parts. First, I'm going to give you an overview to BERT technology, and then we are going to discuss a bit more about language knowledge in BERT, and then we are going hopefully to localize knowledge in BERT, and finally we will conclude some interesting facts. So what is BERT? Actually, first of all, I have to just remind you that this is not a full presentation about the BERT itself, but it's actually we are looking to answer the question, what is inside BERT? So if you are not familiar with BERT and transformer, maybe it's better to go and check and maybe a detailed search about BERT and how transformer works can help you to understand the whole concept of this presentation better. But BERT actually is a stack of transformer encoder layers, and if you are familiar with transformers, you know that the transformer is a very recent technology that was proposed in mostly, I can say, in Attention is All You Need paper by Google. And after that, two major paper was proposed. One of them was BERT by Google, and the other one was called GPT by OpenAI. The first paper just used the BERT paper actually just used only an encoder part of the transformer, and the GPT actually used the decoder part of the transformer. As I have already mentioned, BERT actually is just an encoder transformer, and they, in the original paper, they just proposed two different configurations. One of them was BERT base and the other one was BERT large. BERT base is very similar to the GPT, and they have 12 layers of attention, and the hidden dimension is 768, and they also use 12 attention head. So the total parameter is 110 million parameters, which is quite a small architecture, a small neural network, but considering that the current transformers at least are very huge, and the other one is BERT large, and this one has 24 layer hidden dimension size of 124 and 16 attention head with total number of parameters around 340 million. They trained BERT with two main objectives. The first one is mask language modeling, and the next one is the next sentence prediction. And they trained these whole architectures in two stages. First, they have a pre-training stage, and they train the BERT on a very large corpus, and then in the second stage, they just fine-tune this pre-trained model for different tasks. The other thing that you may need to know about BERT architecture, actually, it's the difference in their embedding usage. They actually add another embedding as the input to the attention layers because of the new structure that they use for the second objective next sentence prediction. So instead to use only one sentence as an input, they use two sentences as input to the BERT neural network, and with two special tokens, actually they just separate these two sentences. So as you can see here, they have a separation special token which just define which just show the network, okay, these are two different segments, and the other special token is a CLS special token which is useful for classification task. And as you can see, the output of the first token is a class label which predict if these two sentences as the next sentence prediction objective, if these two sentences are adjacent or they are not. So as a result, they also add another token, another embedding in the original transformer. We always have the token embedding and the position embedding, but in the BERT paper they also add another embedding called segment embedding, which the only difference is that, okay, for each sentence they have a specific embedding. So as you can see here, it's the embedding of A and embedding of B. So all of these are this embedding of B's are similar vectors. So the neural network can actually distinguish between two different sentences. This is actually a very clever idea to just tackle this kind of problems and achieve the next sentence prediction objective. In the masked language modeling task, they just actually randomly replace one specific word, some words in the sentence, with a special token called mask. So for example, if you have my dog is hairy, there is a high possibility that this just transferring to my dog is a special token mask. But because in the real world, in the test scenario, we don't have this special token as an input, so they solve this problem by reducing the whole probability of being masked to 80% of the time, and in the other 20%, for the 10% of the time they just replace the word with a random word. So my dog is hairy become to my dog is apple. It's possible. And 10% of the last 10% of the time they just keep the word unchanged, and they argued that the purpose of this is to bias the representation toward the actual observed word. And for the next sentence prediction, I just want to give you an example what is adjacent, what is not adjacent. So let's say that we have as input the CLS token, the man, some special token mask to the store, and the separation token and penguin token mask are polite, less BERT's separation. As you can see, these two sentences are not related at all. They are two different sentences, so the label should be not next. Please also consider that this flightless as one word become two different tokens because of the tokenizer that the BERT architecture, that BERT model just utilize, and they will call it word piece. If you are not familiar, I will discuss it later. And as another example, the man went to a store and he bought a gallon of milk. These are absolutely related, and this should be predicted as they are adjacent. So the label should be is next. So what is the tokenizer? Actually, it's a way that we will separate a sequence into subsequences. So let's say that you have a sequence of something and sequence of numbers, and you just separated them with a semicolon, and so the tokenizer can divide these sequences just by finding those special semicolons. And so this divider can be anything. It can be a space in a sequence of words. So by a space you can just separate all the words, or it can be anything that you maybe need. But if you tokenize a very large corpus using the traditional methods, you will come up with a very large vocabulary size. And this can be problematic because you have a very limited computational resource. So you might need, to just come up with an idea to use that computation very efficiently. So some researchers actually come up with an idea called byte pair encoding, which is actually based on an algorithm that was proposed for information theory in 1994. But the researcher in neural machine translation actually used that algorithm to tokenize the words into subword units. But what was their intuition? They actually find out that it seems that in languages, various word classes are translatable via smaller units than words. So it means that we can somehow manage to encoding rare and unknown word classes as sequence of subword units. So for example, if you in neural machine translation, if you consider you have Barack Obama as a name entity, if you are a good translator, you don't need to know what is Barack, what is Obama. You can say that, okay, these are names. And if you are also, a good translator, and you can, if you have knowledge about claustrophobia in English, and if you see that word in German and you have the knowledge of their characters, so you can actually guess that what's the meaning of the claustrophobia. And more interestingly, even for morphologically complex words like solar system in English, which has a very same structure in other languages like German, for example, sound system is actually the combination of sound plus system, which means solar plus system. And you can guess, okay, this is the meaning for this words. And the author called this kind of name entities, cognates and loan words, morphologically complex words, as transparent translation. So they end up with an algorithm which is very useful for tokenization in all natural language processing. So what's byte pair encoding? So the original algorithm actually is a data comparison algorithm. So let's say that we have these sequences or input. So what's the most frequent combination in this sequence? As you can see, we can say that, okay, this AA is the most frequent one. So if you just replace this AA with a new character which is not already in your sequence or in your corpus, then you will come up with this new sequence ZABD ZABAC. And if you are looking into that one, you will see that, okay, the AB now is the most frequent combination in this sequence. So if you want to replace this A new character called Y, then you will come up with something like this, which is more complex comparing to this one. Keeping that in your mind, the byte pair encoding segmentation algorithm is also very similar. So let's say that we have a very large corpus. We just extract all the characters in our corpus, and let's say that it's limited for now, just as an example. And we also extract a dictionary of words that happen into a corpus. Low, it's happened 5 times in our dictionary, lower 2 times, newest 6 times, and widest 3 times. So if you check these words in your corpus, you will see that the most frequent combination in this dictionary is the ES. So why? Because it's happened 6 times here, and ES also 3 times here, so 9 times it is most frequent. So if you just combine this ES and new character called ES in your vocabulary, you will end up with a new corpus. And this new corpus, the most frequent one is the EST. And if you replace EST, you will end up with this EST as a new token. Just consider that this EST now is a new token, and it's different with E, S, and P, which are different tokens. You can continue this procedure until you just satisfied with the number of vocabs. So this is very interesting that in the end you will face with something like this, and you can also even if you have some rare words, let's say that it's wild test, and you can actually have an idea. So okay, it is wild and plus est and plus er, let's say. It doesn't mean something in English, but as an example, you can have a better knowledge. You can have a better idea of what I mean. So now that you know about BERT encoding, you can also be familiar with the tokenizer that was utilized in BERT. They call it word piece algorithm, and this word piece, it's very similar to the BERT encoding. It's slightly different, and the difference is that okay, they will use, instead of frequency, they will use likelihood. And so how they just come up with this likelihood, they are going to build a language model based on all the sequence of characters that they have, and this language model that can give you a likelihood. So they will add a new word unit to their vocabulary if out of all the possible ones, that one increases the most, the likelihood on the training data the most when added to the model. So this is word piece algorithm. And in the end, you will end up with a set of vocabulary similarly as byte per encoding. Now that you are familiar with the BERT architecture, BERT tokenization, and attention and transformers, now we can go to the main parts of the paper. So what is inside BERT? What kind of language knowledge we can find inside BERT? As you know, each transformer, in a standard transformer, you can just extract a feature vector for each encoder output as an embedding vector. So for each token, you're going to have a feature vector that represent that token depending on which layer you want to use. You can use all of these different embeddings. But the question is that how we can use all of these together. Which one is better? If I use the first layer is better, if I use the second layer, if I use the third layer, which one is better? Maybe if I just sum all these 12 layers together, maybe I can achieve a better performance score. Or if I use only the second to last hidden layers, I can achieve better. Or maybe if I just concat these last 4 hidden layers, I can actually outperform all of these techniques. But the solution is different, and you can use it. You can use any combination, any sort of technique that you may be interested. So as you can see here, the performance gain after these, except the first layer, is not so much. So maybe you can just use whatever you like. The most interesting fact that I found in this paper was these key insights that I like to share with you. The first part was BERT representation, or contextualize, which we already expect that. So, the meaning of a word, one specific token, is depend to the whole context. And as we can see, representation of the same words varies depending on position of the sentence, maybe because of the next sentence prediction objective, as argued in Mikus and colleagues in their 2019 paper. But also, later BERT layers produce more context-specific representation. This one is also very interesting, and I think that we also expect that one because higher layer have only access to the previous layer, so they have to come up with a more complex representation. In the previous slide, we just find out that we can use the output of each encoder layer of the transformers as an embedding vector. So, it's useful for different tasks that we may come up in the end in the natural language processing. But it's very interesting that, okay, is there any language knowledge in BERT? It says that there is, actually some authors, they come up with, they were able to extract some parse trees just from the BERT representation. And this one is very cool. I don't know if you are familiar with the parse trees. If you check this example, I'm sure that you will catch a better understanding of what is a parse trees. So let's say that we have a sentence, the chef who ran to the store was out of food. So if you consider this as a sentence, you will see that, okay, the was is actually after the store and is more closer to the store than the chef. But if you are, English, even just an, if you're not even so much familiar with the English language, you can guess that, okay, this is the store that was out of food, or this is the chef that was out of food. If you just, consider that the was is more closer to the store, then you will come up with the fact that the store was out of food. But this is not true. Actually the chef was out of food. Because of that, ran to the store. So the chef who ran to the store was actually out of food. So as you can see in this tree, this kind of relationship was preserved very well. So the distance between the chef and the was is 1, but the distance between the chef and the store the distance between the store and the was is 1, 2, 3, 4. So was has a very larger distance to the store, considering the chef. We can also see the very similar situation in the embedding space of the BERT. And they shows that this is even for large sentence, this is true for both BERT base and BERT large. As you can see in this example, the black lines here are the gold answer, and this one are the prediction first for the BERT base, and the bottom one is the prediction for the BERT large. So they argued that okay, there is some language knowledge similar to human, language knowledge structure that we have, and they shared that okay, BERT representation are hierarchical rather than linear, and BERT embeddings encode information about part of a speech, syntactic chunks, and roles. Also, Liu and colleagues argues that BERT knowledge of syntax is partial because they were not able to, just using the probing technique, they were not able to generate the whole syntax of knowledge, the knowledge of syntax, just for long distance parent nodes. And it means that okay, they just conclude that the BERT knowledge of syntax is partial, but it might be because of the probing techniques that we do already have. So we can come up with syntactic structures not directly encoded in self-attention weights, but they can be transferred to reflect it. So if you are going to directly use self-attention weights, maybe you're not going to achieve similar result, but if you have some sort of transformation, and if you apply the transformation on that one, you can learn, and you can learn a transformation to just use these attention weights to achieve similar result. As you can see also in this example, the goal parse distance matrix is very similar to the predicted parse distance matrix by the BERT, and it's quite interesting to achieve something like that, because the main objective of the BERT is not even related to these things, but it's an unsupervised language model objective, which it's impressive that can in the end come up with something like this. It's interesting also to note that BERT actually takes subject-predicate argument into account when performing the closed task, as argued by Goldberg in 2019. So if you have, for example, this sentence as your input, the keys to the cabinet, and you are going to predict this word on the table, let's say that this is a mask word, and you're going to predict what can be here. Actually, the probability that the R can be here is much more than the probability of the is, because the keys, the subject is plural. So it seems that the BERT actually learned this kind of relationship alongside even with the noun, verb phrase, and nominal subjects. So let's say that we have a sentence. The important thing about Disney is that it's a global, and then the probability of being a brand, and noun here is much more than put a verb phrase here, but here that is after that it can be the probability of verb phrase much more than the noun itself. So although BERT doesn't understand negation, is insensitive to malform input, unfortunately, so no prediction change even with shuffled word order, truncated sentence, remove subject and object, but it's very cool that it can take this kind of information. So in fact, BERT encodes information about entity types, relations, semantic roles, and proto roles successfully, and but also BERT struggled with representation of numbers. They argued that maybe it is because of the tokenization technique that they will use. So maybe this is only because of the word piece tokenization, which makes sense. So This is a quite good achievement by the BERT. In terms of knowledge bases, BERT also is very competitive with methods relying just on knowledge bases. Let's say that we are going to predict that, for example, Dante was born in where, and if you going to use the knowledge of BERT, you can actually correctly predict the phylorons. And as you can see here, this can be in fact true for even all the other sentences. So let's say that the official language of Mauritius is, the probability of being English is much more than the other languages. So even the original language of mon Uncle Benjamin is absolutely French, and the probability of being a French is much more than the others. You can also see other example like iPod Touch is produced by Apple, and the prediction by Apple is much more than for example, Nokia, Sony, Samsung, and Intel. However, unfortunately, BERT cannot reason based on its board knowledge. So, in other words, this means that, okay, although the BERT knows that people can walk into houses and that houses are big, but it cannot infer that houses are bigger than people. So this it's a quite downside, but actually, we do have problem in almost all artificial intelligence, and when the reasoning, when you are going to just do the reasoning, it's a bit more complicated than we can imagine. So actually, it's not only limited to BERT itself, but also we do have this problem, this reasoning problem in AI generally. Actually, it's a very hard problem, so maybe later we come up with a solution, but no, it's not an easy task. But this kind of language knowledge comes from where exactly? Are they come from attention, or they come from different layers? Where this knowledge comes from? So, if you just check the self-attention heads, mostly they will follow this kind of patterns as their output. So it is mostly vertical in the separation token, or it's diagonal on this different token, whatever this sentence can, it can be whatever sentences that you like, but for almost most of them, you will see this kind of pattern, one of these patterns. These are the top 5. So you will end up with a vertical, diagonal, vertical plus diagonal, block section, or heterogeneous. So almost all of them follow one of this pattern. So Kovaleva actually argues that maybe most of these self-attention heads do not directly encode any non-trivial linguistic information, because half of them actually had the heterogeneous pattern. So they argued that maybe this problem is because of overparametrization, but we cannot say, we cannot be sure perfectly. But Clark and colleagues actually define the attention weight by how much a particular word will be weighted when computing the next representation for the current word. Maybe it's a good thing to just remind ourselves that, okay, what is attention by good definition? Some researcher argues that the BERT attention heads, it seems to specialize in certain types of syntactic relations. Even some, the Clark and colleagues identify a BERT head that can be directly used as a classifier to perform coreference resolution on par with the rule-based system, which it is quite interesting. But it seems also no single head has the complete syntactic tree information. So, other researchers even argues that even when attention heads specialize in tracking semantic relations, they do not necessarily contribute to BERT's performance on relevant tasks. So, even, some authors identified two heads of base BERT in which self-attention maps were closely aligned with annotation of co-frame semantic relations, but unfortunately, um, also, we believe that such relations should have been instrumental to tasks such as inference, but a head ablation study actually proved that these heads were not essential for paired success on glue task. So it seems that most of these, heads are not necessary, again, because of overparametrization that we do, always in deep learning. And maybe the ultimate reason is because of the memorization. So almost all of the heads have the same ability, and maybe also because of the drop or that we will use in the attention, this all of these heads will be somehow robust to if you want to just remove one of them, the others can perfectly work. In BERT, lower layers have the most linear word order information, and syntactic information is the most prominent in the middle BERT layers. It is interesting to note that the middle layers of transformers are overall the best performing and the most transferable across tasks. So as you can see in the right figure, they just test. So each column is a probing task, and each row just represents a contextualizer layer, and in BERT base and in BERT large. So it is obvious. You can see that almost always, the performance in the using the middle layers is much more than the even the last layers or the first layer, obviously. It seems that this is true even for all the transformers structures, but you can use the final layers of BERT for task specifics settings. So the final layers of BERT are the most task specific, which is reasonable, because almost always you're going to fine tune those last layers for one specific task, and it seems that the last layers are going to keep the much more specific information, which is in fact it's true almost in all the deep learning architectures that we have, I think. In the next section, let's go back to the very important part of uh, the whole training procedure of the BERT, which called pre-training. So it's very interesting to note that some authors actually come up with the idea that, okay, if you just remove NSP, it does not hurt or even slightly improves task performance, which is quite awesome because it's a bit counterintuitive. We maybe thought that, okay, this next sentence prediction is very essential for the whole learning, and intuitively we can support the next sentence prediction. It looks very cool, and almost we can say that, okay, almost all of us believe that this next sentence prediction can help the model to train better. But actually these authors just claim something else, and it seems that the result shows, okay, this is the fact. Even the same author actually suggests that using dynamic masking instead of static masking can improve BERT's BERT's mass language modeling, but their result doesn't support them very well. It's not so much. It's not a huge improvement, although there is some improvements. Some other researchers also just integrate external knowledge into the BERT architecture something like entity embedding that was, that you can find in eBERT and ERNI. So even, some other authors just integrate semantic role information with BERT representation, which all of these are interesting, and we can follow up with them. But generally, the performance improvement is not that much that, okay, we just follow maybe a more complex methodology. But the main question that we might ask here is that why we need two-stage training? Why we just don't go directly train, an end model just for one specific task? It seems that, actually this pre-trained weights help BERT to find wider optimize fine-tuning, at least on this specific task, than training from scratch, which make it easier to go, and learn something. Even it become faster, so you can optimize your objective so much faster. Generally, about the BERT architecture and their design, the authors also argues that, based on the other papers, they showed that, okay, the number of heads was not as significant as the number of layers, and some other authors just showed that larger hidden representation size was consistently better, but the gains varied by sitting. This one is absolutely, maybe we can expect that one, because generally in deep learning, if you increase the size of the model, you will end up with a much more powerful and much more powerful model, and the capacity will be increased. So your model generally can memorize better and can maybe learn better. And so, but counterintuitively, I can say, because we generally use the term mini batch, but it seems that they use instead the large batch training. And by large batch I mean 8K, the other authors 32K. It seems that this improves both the language model perplexity and downstream task performance. It's a bit counterintuitive, but it's very cool, because it just, if you can manage to hold such a mini batch in your memory, which is a big challenge, but you can optimize your model so much faster. Another interesting result that was shown by Zhu and colleagues in 2019 was also interesting, because they considered that the embedding vector of CLS is not normalized, so they just normalize it, or they just centered the vector of CLS around 0. It seems that if you do these things, you will stabilize the whole training, and so as a result, this will leading to a performance gain on text classification tasks, which is quite desirable. About the overparametrization in the BERT, and why really recent techniques like knowledge distillation and quantization can efficiently compress BERT. They also suggest that all but a few transformer heads could be pruned without significant losses in performance, which is quite expectable, and most heads in the same layer of BERT show similar self-attention patterns. This is interesting, because it seems that because we will pass all the output of all self-attention head in a layer pass through the same NLP. It seems that all of them in the end will just achieve the same information, which maybe we need to come up with a different technique so we can solve this problem, because it's not desirable to have multiple similar things. So it seems also, depending on the task, some BERT heads or even layers are not only useless but also harmful. This one is very interesting, and because we didn't expect that it can also harm the performance to the downstream task performance, which is quite interesting. And so maybe later someone come up with a solution that okay, how we can make sure that all of the BERT heads and layers can be useful for the downstream task performance. Also, Clark and colleagues in 2019 suggest that one of the possible reasons why BERTs end with redundant head and layer can be use of attention dropouts, which is reasonable because the whole idea behind dropout is to make the whole models more robust. One of the very interesting part of the paper that I really found out interesting is this table, because they just come up with a very clean table that just shows different technique for compressing BERT. It's like distillation, quantization, and all the other methods that tries to just compress the BERT and come up with the same performance or a bit less performance, but with a gain up on speed up. So as you can see here, even one of the models actually achieve 400 times better speed than the BERT itself, but just losing maybe 9% performance, and which is amazing, I can say. It shows that how much BERT has redundant parameters, and how much we don't use our resources efficiently in the current deep learning approaches. Even in the paper, all BERT, the 2x large, which is it's a bit less. The speed up actually is less than the original BERT, but the performance gain is a bit better. So maybe they actually increase the state of the art with 7%, and the compression rate 0.47, which is again less than the original BERT. But as you can see, different authors suggest different approach. They use different metrics, and they also use even some of them use smaller vocabulary size. Some of them use the reduced version of the dimensionality of the hidden layer, and some of them also use the dimensionality of the embedding layer, a reduced version of the dimensionality of the embedding. So as you can see here, there are so many papers out there that just use the BERT, and they just try to improve it somehow and to gain some advantages. As another attempt, some authors also suggest multilingual BERT or MBERT that was trained on Wikipedia in 104 languages. And it seems that the result is very interesting, because although the models, although actually you didn't give the multilingual BERT any idea about the languages, so there was no language IDs in the training procedure, but it seemed that multilingual BERTs encodes language identities, which is interesting. As you can see here, the more similar languages like Persian, Punjabi, or Urdu are more closer in this embedding space to the other languages like Roman, Slavic, or even here Germanic languages are here. Even here you can find Tatar and Turkic languages, which is very similar considering the other languages. So as you can see here, the BERT seems naturally learn high quality cross-lingual board alignments. And except in language generation, BERTs perform surprisingly well in zero-shot transfer on many tasks. And it seems that it is not necessarily to retrain all the BERTs for different languages. You just need to freeze the whole transformer base, and if you just retrain only the input embeddings, you can achieve very good results, which is quite interesting, and I didn't expect that one at least. And in the end, authors suggest three different, you know, uh, things to maybe later researcher should focus on these things. So it seems that the lack of a benchmark that require verbal reasoning is necessary, is can be filled, and while BERT both performs almost, you know, any other traditional methods, and it's the state of the art in NLP benchmarks. But it seems that a growing list of analysis papers also shows that its verbal reasoning abilities are not as impressive as it seems. So it seems that we have to come up with a benchmark that require verbal reasoning. And also we have to, in the end, we have to, teach this kind of model the ability of reasoning. It's a difficult task, but there's nothing that we cannot achieve as a human. So hopefully very soon we can have some models in AI that's able to reason very well based on, at least based on their knowledge. In you know specifically in deep learning, I think we need something like that. And as the last part, it seems that we are not necessarily sure that's what's going on in the inference time in the BERT. So at the moment, we know that the knowledge in BERT does not necessarily get used in downstream task, but we don't know exactly what happens at inference time. I hope that you enjoyed my presentation, and it's helpful for you. And if you have any suggestion, comments, or whatever you like, you can contact me. And thank you so much for listening. Please stay safe and healthy. MojtabaValipour, University of Waterloo.